Hello and welcome back, wonderful people. Today we are looking at the page that has Atwood again at the top of it. This is an example of two masses acting on a pulley that also has mass, which means we are still applying Newton's second law, except now again for a solid object that's in rotation. In our example problem, we have a pulley of mass 3m and radius r is mounted on frictionless bearings and supported by a stand of mass 4m at rest on a table as shown. The moment of inertia of this pulley about its axis is rotational inertia is equal to 1.5 mass times radius squared. Passing over the pulley is a massless cord supporting a block of mass m on the left and a block of mass 2m on the right. The cord does not slip on the pulley, so after the block pulley system is released from rest, the pulley begins to rotate. If we look at the masses, we recognize that the pulley is probably going to be rotating clockwise, so there's a very good likelihood that we're going to want to call that the positive direction. In part 1, on the diagrams, draw and label all the forces acting on each block. So we're specifically looking at just the hanging masses at the moment. The forces acting on the block of mass m would be the force of gravity 1. And then since there's a string attached to the top, we would have a tension force going up toward the pulley. For mass 2, this mass is twice the mass of the original, or the one on the left, so that's going to be force of gravity 2, and then we will have a tension force that is not the same as the force of tension 1 because this is not a massless pulley. Because this thing has an actual mass, it's requiring torque to make it rotate. In your images, make sure that your force of tension 1 is a little bit bigger than your force of gravity 1 because we have acceleration going upward. And in your block number 2, we have acceleration going downward. So we want to make sure that the force of tension 2 is slightly less than the weight of 2. Now let's see what we can do with this. In part B, we use the symbols identified in part A to write each of the following. First, the equations of translational motion, i.e. Newton's second law for each of the two blocks. The sum of the forces that are acting on block 1, remember that we said we were calling upward as positive on the left and downward as positive on the right. So the forces acting on block 1 would be the force of tension 1 minus the force of gravity 1 is equal to the mass 1 times the acceleration. Because the force of tension is what's applying the torque, I'm going to go ahead and solve this for force of tension. Force of tension 1 is going to be equal to the mass of 1 times the acceleration plus the force of gravity, which is mass 1 times gravity. Then I'm going to do the same thing for the forces that are acting on mass 2. In this case, the downward direction is positive, so force of gravity 2 minus force of tension 2 is going to equal mass 2 times the acceleration. I'm going to go ahead and solve this again for force of tension. So force of tension 2 is equal to mass 2 times gravity minus mass 2 acceleration. And we're going to keep a hold of these two equations because they are going to be useful to us in a moment. In part B2, we want to do the analogous equations for the rotational motion of the pulley, which means we're talking about torque. Let's first identify the direction of motion, which we know that the cord is going to be moving in the clockwise direction because the mass 2 is heavier. So I'm going to call that direction positive. We also know that the axis of rotation is about the center of the pulley, which then tells us that if we consider the force of gravity or the weight and the normal force, both of those are acting at the axis of rotation, which means that there's no radius, which means that there's no torque being applied by either one of those. That leaves us with just the tension forces. So our torque is going to be coming from the tension force associated with tension force 2 minus the torque associated with tension force 1. And that's going to be equal to the rotational inertia times the angular acceleration. We know that our torque equation is R sine theta times force. In both of these cases, the radius is 90 degrees in relation to the force. So our sine theta is sine 90, which is going to be 1. And so I can show that the sum of my torques is equal to the radius times the force of tension 2 minus the radius times the force of tension 1 is equal to rotational inertia times angular acceleration. In part C, I need to combine all of these wonderful equations and do a bucket load of algebra to solve for the acceleration of the two blocks. The first thing that I'm going to do is I'm going to plug in all of this for force of tension 1 and all of this for force of tension 2. I'm also going to bear in mind that mass 1 is a single m and mass 2 is 2m as I incorporate them into the overall equation. That's going to look like radius times the force of tension 2 is m2g, which is really twice the mass times g, and then minus m2a, which is 2m times acceleration, minus r times mass 1a is just a single ma, plus mass 1g is a single mg, is equal to I times angular acceleration. Next, I'm going to pull out my r from both of these components and combine like terms. So I have r times 2mg minus 2ma minus ma minus mg is equal to rotational inertia times angular acceleration, which then gives me r times mg minus 3ma equals I times angular acceleration. And I remember that from my beginning part of my question, all the way back at the beginning, they told me that my rotational inertia was equal to 1.5 or 3/2 mr squared. And I know that tangential acceleration is equal to angular acceleration times the radius. So I'm going to take all of these things and plug them in. The rotational inertia is going to go here. The angular acceleration is tangential acceleration divided by r is going to go here. And then we can start combining things to solve for the acceleration that we're looking for. So we'll have radius times mass times gravity minus 3 times mass times acceleration is equal to 3/2 mass times radius squared times acceleration over r. Connecting everything again, we get r times mg minus 3 mass times acceleration is equal to 3/2 times mr squared acceleration over r. On this side, on the right side, I see that I can cancel out one of my r's, which is going to leave me with a single r on both sides, so I can actually cancel out both of them by then canceling out r here with r here. Now I'm at mg minus 3ma is equal to 3/2 ma, and I can combine like terms to give me mg is equal to 9/2 ma. At this point, both masses cancel out, and I will find that my acceleration is equal to 2/9 of gravity. Now I want to determine the tension force in each of the two strings. To do that, I'm going to use the equations that I used to determine the force in part B and the acceleration that I calculated in part C. The force of tension 1 is equal to the mass 1, which was mass, times the acceleration, which was 2/9 gravity, plus the mass times the gravity. If I pull those all together, I end up with mass times 2/9 gravity plus 1 gravity, which gives me 9/9 plus 2, so 11/9 gravity times the mass. Force of tension 2 is a very similar setup. Mass 2 times gravity, only mass 2 we know is 2m times g, minus mass 2 times acceleration, so that's 2m times 2/9 gravity. And to simplify everything here, I'm going to pull the 2m out first, and that's going to give me gravity, which I'm going to call 9/9g, minus 2/9g, which is then going to give me 2 times the mass times 7/9 gravity, which is then going to give me 14/9 mass times gravity for force 2. For the last part, we're looking at the normal force associated with the apparatus by the table while the blocks are in motion. So what we're really looking at is the masses of all the components, each mass, the pulley itself, and the stand. So what normal force would exist to support those in the opposite direction? If we summed the forces and we said that these were in rotational equilibrium, then we would have the force of gravity on mass 1 plus the force of gravity on mass 2 plus the force of gravity from the pulley plus the force of gravity from the stand. And that whole system would be equal to 0 if it was at rest. However, since this thing is not at rest, this doesn't work. We have to consider, instead of the force of gravity of the two masses, we have to actually think about the force of tension that's being applied by the two tension forces. So force of tension 1 plus force of tension 2 plus force of gravity of the pulley and force of gravity of the stand. We've already accounted for the acceleration by using the tension forces, and so we can simply sum all of them up. The force of tension 1 we calculated in part D was 11/9 mg. The force of tension 2 we calculated as 14/9 mg. The force of gravity of the pulley, well, it says that it is a mass of 3m, and since we want these to have the same denominator, 3 times 9 is 27/9 mg. And then finally, the force of gravity of the stand is 4 times the mass. So 4 times 9 is 36/9 mg. When I add all of those together, I end up with 88/9 mg. If we compared that to the object at rest, we would have mass times gravity plus 2 mass times gravity plus 3 mass times gravity from the pulley, and then 4 mass times gravity from the stand, which would give us 90/9 mg, or 10 mg. But because the object is accelerating, we can't use the entirety of the force of gravity for each of our components. You can see that we're missing 2/9 mg due to the acceleration, and our normal force ends up being this instead of 10 mg. I highly recommend looking over a couple of other 2-mass pulley type problems or other Atwood type problems that are using a massed pulley instead of a non-massed pulley. Have a fantastic day.